Right. So hi everyone. Welcome to this seminar of the Clever Planet Fall 2022 seminar series. My name is Maxime Maurice and I'll be your host today because the planned host is late. I'll start giving you a brief introduction about the Clever Planet project as well as an acknowledgement, and then we move on to the introduction of our speaker today, who will eventually get the floor. Let me share you the slides that I just Drew, can you stop sharing the okay, and of course I have issues with my computer, so I will probably not be able to share the introduction slides, but it doesn't prevent us from doing this introduction as we usually do. So actually, Drew, you can probably reshare directly, and I'll do the introduction. Okay, so as those of you who have been with us for a few previous seminars might know, the Clever Planet is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University, and it is supported by NASA as one of the teams in the Nexus for Exoplanetary System Science Coordination Network under astrobiology. And now a land acknowledgement. So our research at Rice University is pursued on the traditional lands of several native peoples, namely the Karankawas and the Sanas, as well as the Coahuiltecans, represented today by the Tapilam Coahuiltecan Nation, and the Aishaks, represented today by the Atacapa Aishak Nation. We see as our duty to acknowledge these historical aspects of our identity and to foster a beneficial environment for all communities, particular those who preceded us on this land. All right, and that's my great pleasure today to introduce you Professor Drew Syverson, who's going to give the seminar today. So Professor Syverson is from the University of North Carolina, Charlotte. He received his PhD from the University of Minnesota and held a postdoctoral fellowship at Monash University and Yale University. Drew's work span a broad range of topics between ocean hydrothermal vent chemistry, geobiology, non-traditional stable isotope geochemistry, and ore mineralogy. His talk today is entitled Exploring the Chemical and Physical Controls on the Bioavailability of Nutrients Delivered to Seawater from Seafloor Hydrothermal Environments. I will remind you that if you have questions, you'll be able to ask them at the end of the talk. And if you're afraid you're going to forget them, you can write them down in the Q&A session and we'll read them to the speaker. So with that, Drew, the floor is yours. Take it away.
Thanks for the intro, Maxime. Appreciate it. I'm just going to go full screen. Everyone can see that, correct? Yes?
Yes.
Okay. So thank you, everyone, for listening to me today. I really appreciate being here. This is a great opportunity for myself, and I really like the organization and the diversity of scientists that are actually being involved with this. So I appreciate your time. So first of all, I want to acknowledge some of my colleagues from a number of universities here. So Yale University, Calgary, University of North Carolina, mostly my undergraduate researchers, Monash University, and the University of Minnesota, where I learned a lot about hydrothermal geochemistry in the first place. And also, I would like to thank my colleagues at Yale who got me involved with understanding water worlds better. And that's with the Alternative Earths team. And also, I want to thank you to the Clever Planets team here at Rice University. So I appreciate it. All right. So today I'm going to talk more about water worlds that are more Earth-like. And so, for instance, we have modern Earth on the left here, which is the big blue marble in the ocean or in the universe or our own solar system. And then on the right is what we would expect maybe for early Earth and also for rocky water worlds, where it's not an extensive ocean like 100 kilometers thick, but less than that. And the processes that I'll be focusing are mostly on hydrothermal processes. And so what you see here is a figure of the geothermal heat flux globally. And you can see that most of the heat that's actually left from mantle heat flux is actually dissipated is along the mid-ocean ridge axes. In particular, about 90% of the heat that is lost is actually from off-axis hydrothermal fluxes, whereas the remaining high temperature on-axis hydrothermal flux accounts for about 10% of that. So I'll be focusing on both the on-axis hydrothermal flux and the off-axis hydrothermal flux environments. And so, as I said before, we'll be focusing on hydrothermal processes, but trying to understand how mantle heat flux and seafloor spreading may have an effect on the magnitude of the processes happening in the subseafloor, and also how atmosphere and oceanic chemistry has an effect on what's happening at the seafloor, and how that influences planetary habitability. In particular, we're going to be focusing on nutrients such as phosphorus and metals such as iron and copper that are fluxed to seawater, primarily due to the ocean crust being altered. So overall, there's two main topics I'll talk to you all about today. I'll try to get through it not too quickly so you'll understand well. The first one is trying to understand the physical chemical controls on metal and sulfur mobility in the subseafloor of mid-ocean ridge hydrothermal environments. And then the second topic is more about the weathering of the seafloor and how phosphorus can be bioavailable depending on whether the ocean's anoxic or oxygenated. All right, so starting with the on-axis hydrothermal flux, the mid-ocean ridge hydrothermal systems. So right now, this is a map of the global distribution of hydrothermal systems. There are way more than what you actually see with those dots here. But these are the locations of vent fluids that we used in this analyses. And what I do is I have them binned by color, depending on their mid-ocean ridge spreading rate. So the red dots are slow, so less than 40 millimeters per year. Intermediate, it's about 40 to 80 millimeters per year. And then fast mid-ocean ridge hydrothermal systems are greater than 80 millimeters per year. And then on the bottom right shows you the relative abundance of each of the slow, intermediate, and fast mid-ocean ridge hydrothermal systems. So this will be my basis for this analysis for the first part of the talk. So as we all know, I hope so, at least, that mid-ocean ridge hydrothermal systems are a very unique environment on the seafloor. And they are host to extremophiles, and they deliver nutrients to seawater. And so you see on the left image here, there's a black smoker that's being sampled by a titanium sampler that's connected to the robot here, which I believe is Elvin, or actually is Jason. And on the right, you actually see it has a suction, basically some type of vacuum that can actually collect organisms. But what I really want to highlight is that those black smoker fluids, they deliver a lot of metals to seawater. And so here on the right, there's a geotraces transect where they took samples of basically seawater compositions or seawater concentrations of metals such as iron along that transect, which is described by that arrow. And below, you can see actually the heat map of dissolved iron concentrations. And the mid-ocean ridge axis, which is shown as 0.18, has a very high concentration of iron compared to background seawater. So, and just to give you an idea of just the structure of the subseafloor along at least magmatically active mid-ocean ridges, is that you have a layer of pelobasalts on top. Below you have the zone of sheeted dikes, and below that you have basically gabbro. But between the gabbro and the sheeted dikes is this zone denoted as the reaction zone, which I have here as an RZ on the left y-axis of that left figure. And below the reaction zone is actually where the axial magma chamber exists, which actually provides the heat that fuels the hydrothermal circulation. The figure on the right is just to give you an idea of just the amount of magmatic activity that takes place as a function of spreading rate, and that most from slow, intermediate, and fast are magmatically active, whereas slow do have more of a tectonic control as well. But in this talk, we're only talking about magmatically basalt-hosted mid-ocean ridge systems, nothing ultramafic. Okay, and the fluid chemistry that we will use for this analysis is basically from the Deal-Bach hydrothermal database. And once again, those dots on that map represent the fluids that we sampled and which we will use for this analysis. And in particular, of those vent fluids, we only take fluids that are greater than 300 degrees C, and we record and use their dissolved chloride, silicon, calcium, sulfide, iron, and copper concentrations. And just to give you an idea of the number of samples we have, that figure on the bottom right is showing us chloride distributions of vent fluids. And we're only using vent fluids that have undergone phase separation or boiling, in other words, in the subseafloor. So those are represented by vapors. And you can see that they are predominant relative to fluids that are seawater-like or more briny. And there are about 197 samples that we use. So just to give you an idea of just how vent fluid chemistry changes as a function of mid-ocean ridge spreading rate, we have H2S, iron, and copper concentrations on the y-axis here. And if you just look at all of them broadly, you can see that there's a general trend where vent fluid concentrations of these components increase with increasing spreading rate. And we'll get back to this a little bit later. And then what we're really interested in this talk, actually, with this part of the talk, is the reaction zone conditions. And so what we measure from the seafloor is an integrated expression of what actually happens during the flow of the hydrothermal fluid towards the seafloor from the reaction zone. But since we can't sample the reaction zone fluids directly, we perform this modeling analysis to actually estimate those concentrations and heat content. And so the way we do so is that we use the measured silicon and chloride concentrations to actually determine the temperature and pressure of the reaction zone. And this has been pioneered by Fontaine et al. In 2009. And it has been used on many other localized studies, but this is the first time it's done on a global scale. And then what we do afterwards, since we have the reaction zone PT conditions, we then estimate the reaction zone fluid composition and the heat content. And once that analysis is done, we compare the reaction zone chemistry and heat content relative to the vent fluid chemistry and heat content. All right. And so here are the first round of results here that you see is that with regards to the reaction zone pressure and temperature, pressure is figure A and temperature is B, is that the fast mid-ocean ridge spreading reaction zone environments actually have lower pressures and temperatures relative to slow and intermediate. And if you convert the pressure data into depth, knowing the density of these fluids, you can actually compare the depth of the reaction zone below the seafloor relative, I guess, via the geochemical methods that we're showing here, relative to geophysical seismic methods, which actually indirectly measure where the axial magma chamber is below the reaction zone. And so the dots on the left represent our estimates, whereas the geophysical estimates are as the diamonds. And you can see here that they all cluster relatively well to each other, implying that the reaction zone is close to the axial magma chamber in these magmatically active hydrothermal environments. And another thing that I should note is that you see lots of scatter here with regards to where the reaction zone and the axial magma chamber exists. And that's solely due to the waxing and waning of magmatic activity in the subseafloor, and that'll have a direct impact on where the reaction zone and the axial magma chamber will exist. Okay, and so what we also do is that since we know the fluid chemistry and the the pressures and temperatures of the reaction zone fluids, we can determine the enthalpy of those fluids and compare it to the enthalpy of the vent fluids at the seafloor. And what you see here is a trend from fast to slow on the left figure, where you can see that there's more heat that is lost with slower spreading rates of the mid-ocean ridge. And so that just basically implies as that fluid goes up from the reaction zone towards the seafloor, it loses a significant amount of heat. But if you actually know the reaction zone depth and the subseafloor heat loss, you can take you can divide those two and you can actually get the heat loss gradient. And they all cluster pretty much at the same heat loss gradient, implying that actually the depth at which the reaction zone is below the seafloor will have a direct effect on how much heat that is lost. So this is very important with regards to the solubility of, say, metals and sulfur and fluids during the upflow towards the seafloor. So sorry for a lot of the figures, but I've already shown you the top 3 figures for vent fluids, where there's a general trend of increasing concentrations of those vent fluids from slow to fast. But with our estimates of the reaction zone fluid chemistry, which is D through F, you can see what our estimates are for sulfur, iron, and copper. With regards to sulfur, it remains fairly invariant with regards to concentration, whereas you can see with iron and copper, there's a general increasing trend of more iron and copper with decreasing spreading rates. So slow and intermediate systems have more iron and copper than fast in the reaction zone. But this is hard to compare. And so what an easier way of doing so is using this relationship of just F, which is the fraction of those dissolved components remaining. And the way to calculate that is just the vent fluid concentration relative to the reaction zone concentrations of those components. And so you can see here for A, B, and C, which is sulfur, iron, and copper, is that the fraction remaining of those components decreases with decreasing spreading rate, meaning that there's a lot more of the iron, sulfur, and copper removed from the upwelling fluids from the reaction zone towards the seafloor as you decrease in spreading rate. And that's mostly due, once again, to the depth at which the reaction zone is below the seafloor, as we've shown before. Now, we can convert this data onto a global scale such that we can have an understanding of how much of these components actually remain in the subseafloor. And so what we did is that we took hydrothermal H2O fluxes from Coogan and Dasso in 2012. And then we also used the global distribution of mid-ocean ridge hydrothermal environments from slow, intermediate, and fast. And then we're able to calculate how much of those components remain in the subseafloor and don't reach it to seawater from vent fluids. So what you should mostly take note of here is that the vertical dashed lines are previous estimates by Alt and Hannington, where you can see that our model results coincide well with their estimates, which to us suggests that this modeling approach is robust. But if you take a step back from what I just showed you on the global amount of subseafloor mass accumulation rates, but look at it as a function of mid-ocean ridge spreading rate, you can see that there's general trends once again, whereas sulfur is more or less within the same magnitude of slow, intermediate, and fast, whereas iron and copper show a clear trend where you're actually having more of those components remaining in the subseafloor and slower and intermediate environments relative to fast mid-ocean ridge hydrothermal systems. And just to give you just the counter example, if we know the global water fluxes from these high temperature hydrothermal systems, and we know their iron concentrations or copper and sulfur, we can then calculate the vent fluid fluxes. And so once again, you can see from this analysis is that copper, iron, and sulfur are fluxed from fast mid-ocean ridge systems to seawater more so than slow and intermediate. Now, this is great and all. It basically confirms that our model is more or less robust, but I think with regards to like the implications and future work, it would be really cool to apply these methods to how changes in the mid-ocean ridge spreading rate has changed through time. And so just to give you an example, and I have not like done further analysis into this yet because it's still an ongoing project. But if we look at the top left figure representing the modern relative abundance of these different spreading environments, and then compare that to what they estimate in about 140 million years ago, so you can clearly see that there's a lot more fast spreading mid-ocean ridge environments. Now we apply the same basically concepts and constraints from our previous analysis of the modern. We can then determine what the actual change in fluxes to seawater is with regards to sulfur, iron, and copper. And we can also determine how much of that remains in the subseafloor as a function of time. So just to give you an example, and there needs to be some more background to confirm these types of analyses here. But basically, if we know the change in the distribution of basically slow, intermediate, and fast through time, we can then calculate how much that would change from the modern. And so positive and negative from 0, there is the vertical or the horizontal dashed line. And then copper, iron, and sulfur on the x-axis. So you can see here with more fast spreading mid-ocean ridge environments, you will actually have basically less subseafloor precipitation of those components, and actually a greater amount of those components flux to seawater. And so I think this is a really powerful tool, and this will be part of my future work here in the next year. So just to summarize this part of the talk, is that the reaction zone depth of the mid-ocean ridge and hydrothermal fluid heat loss is a strong function of spreading rate, and that ore deposition primarily occurs within the oceanic crust, where the maximum drop of sulfide mineral solubility occurs during the outflow of hydrothermal fluids towards the seafloor. And I didn't actually highlight this earlier, but just through doing thermal balance relationships, we've ruled out basically that adiabatic cooling was a significant mechanism for this subseafloor cooling. But in fact, it was actually, we've deduced that it's mostly due from conductive heat loss, and that's near the Pello dike transition zone in the subseafloor. And then the third point is that changes in the relative distribution of slow, intermediate, and fast mid-ocean ridge systems results in changes of the amount of subseafloor sulfide deposition and the flux of metals and sulfur to seawater. And so I just have an iceberg on the bottom right there, just to kind of give you what I like envision with what happens here at the mid-ocean ridge axis, is that most of those metals remain in the subseafloor, where only a minor component actually reaches seawater, or at least the seafloor. So thank you for that part. I'm moving on. So back to this figure here. So during my time at Yale University, I got really involved with basically basalt weathering experiments and how nutrient bioavailability basically changes as a function of atmospheric oxygen concentrations. And so a lot of studies previously, before this work was conducted, ruled out that water worlds were places that were habitable, just because the fact there's very little continental weathering which provided phosphorus to the oceans, and that submarine weathering of the oceanic crust was an effective sink. And we got that basically from inference of the modern Earth. So I basically did an experimental study to investigate this, if that's actually true. So just as a reminder of where we are, we're going to be focusing now on the off-axis hydrothermal flux. And so this basically is the area where it accounts for most of the heat loss from hydrothermal activity. And this is actually where most of the exchange of components between seawater and the oceanic crust takes place. Okay, so this is kind of our idea of the basically the oxygenated Earth scenario for the phosphorus cycle, where most of it's actually derived from weathering of continents, weathering of apatite minerals, which provide the phosphorus to seawater for biological productivity. And that biological productivity then allows oxygen to accumulate in the seafloor, or in the atmosphere, as a consequence of organic carbon being buried. But if you look on the bottom right, where it says basaltic weathering, you can see that seawater, when that reacts with basalt, it may release phosphorus, but then that phosphorus is immediately scavenged onto iron oxides. And that effectively causes marine weathering, at least in the modern, to be a sink, a significant sink of phosphorus to the biosphere. So zooming in to that ridge flank area. So here we are, there's this big orange circle. And so I was talking about previously the high temperature hydrothermal flux of iron, but we're actually now looking at more of the lower temperature hydrothermal environment that's represented by the ridge flanks. And so what happens here is that the seawater will circulate through the oceanic crust and then oxidize the iron that's within primary silicate minerals. And that oxidized iron becomes iron oxide minerals, which then has a high capacity to scavenge phosphorus that may be released from this weathering process. So there was a classic study in 1973 by Bob Brunner, where he wanted to basically test whether seafloor weathering was a sink or a source of phosphorus to the biosphere. And so he reacted basalt, water, and oxygen with a reservoir of a fluid that had dissolved phosphate within it initially. And so, as you can see, with reaction progress with time, that the phosphorus concentration, which is on the y-axis, decreases with time. And that's mostly due to iron oxides absorbing the phosphate, removing it from the solution, therefore not bioavailable. And so just as an example, here's some mid-ocean ridge basalt that we got from the Juan de Fuca Ridge. And here's some microprobe images of iron and phosphorus. And if you can see on the top right of both the images for iron and phosphorus, you can see that lining the silicate minerals, you have high concentrations of iron, which we presume is iron oxide minerals, which we then shown with synchrotron analyses, but I did not show that here today. But most importantly, that you can see that the phosphorus also is in high concentration in those areas where there's high concentrations of iron. So basically, this is the modern example of where the phosphorus goes and seawater reacts with it, with the salt. So what happens though if you actually remove oxygen from this reaction, such that the basalt reacts with the water? What happens to phosphate? What is its fate? Does it be absorbed or does it go into solution? So just to kind of give some background on this, is that there was a significant period of time in Earth's history where there was very low concentrations of atmospheric oxygen. And that also means for oxygen concentrations in seawater. So it suggests that there is a period of time where that process of oxidative weathering of basalt may not happen as extensively. So here's that basalt again. So here's just an image of kind of some reactors, but I actually performed these experiments in an anoxic Coy chamber. But what I did is I pre-treated this basalt. I removed the glass and just stuck with the crystalline components. And I removed the iron oxides that were there already through a reductive dissolution treatment. We can talk about that later. And then I used that powdered basalt as reactant for my anoxic weathering experiments. So here's just the design of the experiment. So the head space of this reactor is very reducing, where it has a high concentration of hydrogen and the remaining gas is nitrogen. And within it, there's a synthetic seawater, which will react with the basalt. So this is completely anoxic in a secondary chamber that also has that same gas composition. And we take advantage of silicon isotope tracers to quantify how much basalt has actually been weathered or dissolved or reacted. And so natural basalt has a 29-28 ratio, 0.05. You can see that on an abundance diagram there on the left as well. But we actually made a synthetic seawater solution that actually has a silicon isotopic composition that is 100, so much different than the natural abundance of silicon. And so this 29-28 ratio of silicon is 100. And we use this as a tracer to quantify salt dissolution. And what we do is that we take samples of time to determine the change in the silicon isotope composition. We also measure the change in phosphorus and metal content of the fluids with time and compare the two. So this is what you'd expect with reaction progress, since there's so much silicon and basalt relative to the synthetic seawater, is that your 29-28 ratio will decrease with time. And that is a proxy for reaction progress. So here are the experimental results. So just as I've shown you before, you see this general trend of decreasing in the 29-28 ratio towards natural abundance of 0.05. So that's giving us an idea of how fast and how much of that basalt's dissolving with time. And then what we do is that since we know the 29-28 ratio change and the concentration of silicon in the fluid, we can determine how much basalt has actually been dissolved and how much silicon has been released from basalt into the reactant solution. And then last but not least here, I also show here the phosphate and iron concentrations with reaction progress. So reaction progress increases to the right. And you can see here that iron and phosphate both increase with reaction progress, and they both release at the same expected amounts as you would expect for the Morb composition of that Juan de Fuca Ridge basalt. And that suggests to us that phosphate and iron are actually behaving conservatively during this weathering of basalt and not being formed as iron oxides and scavenging of those phosphate as a consequence. Okay, so since we know how much basalt has released silicon and phosphate, we can then look at this relationship to determine basically what is that slope here, so we can use it for modeling. And so here is just a regression of this data, and you can see that the phosphate to the change in phosphate relative to the change in silicon with time is around 4 micromoles per millimole. We're going to be using this for some modeling efforts, and I'll show soon. But most importantly, we can convert this reaction from silicon to CO2 by using a modified Urey reaction, which we have it in terms of magnesium just to represent oceanic crust composition. So basically for every silicon that you release through weathering, you've consumed 1 mole of CO2. And we're going to use this next year. So basically this ratio of 3.99 plus 1.03, we compare that of our experimental results to basically what you'd expect for the amount of phosphate released from continental weathering, which is represented as modern rivers. And you can see that basalt weathering actually is just as good as releasing phosphate basically from weathering as continents, as long as it's anoxic and there's no iron oxides being formed. And we take that phosphate to CO2 ratio of our experiments, and we use that with a Monte Carlo analysis to then estimate the oxygen fluxes as a function of CO2 degassing. And so that's what the x-axis represents, CO2 flux from degassing, which drives weathering. And then on the y-axis is the oxygen flux released from the biosphere. And you can see here that with our model or our experimental constraints, we can actually produce a significant amount of oxygen that's fluxed to the atmosphere with even low amounts of CO2 being fluxed or from degassing. And we can get basically fluxes that are within magnitude of the modern and the Proterozoic for a given range of CO2 fluxing. Okay, so that basically changes the picture here. So I highly recommend that basically Gabriele Filippelli, he wrote a really nice commentary on my experiments that's in GRL, and basically he does a really good synopsis of it. So if you get the chance, take a read it. But basically the whole picture now changes. So you don't necessarily need continents to weather to provide phosphorus to the biosphere, as long as the deep ocean's anoxic. And so the seawater will then react with the basalt, release phosphate or phosphorus to seawater, which is now bioavailable, which can be used for biological production. And we can accumulate oxygen in the atmosphere while we bury our organic carbon. But we should really consider on a long time scale is the feedback mechanisms between phosphate release and oxygen accumulation. So as we degas CO2 to drive weathering, the anoxic weathering process at the seafloor will allow phosphate to go into seawater, then becomes bioavailable. That organic carbon buries. You generate and accumulate oxygen in the atmosphere, which then equilibrates with at least the surface oceans over some course of time. But really, what we don't know at this point is how much oxygen do you need in seawater to shut off this source of phosphorus and have it be a sink of phosphorus when you're weathering the oceanic crust. And this is just a blurb that I wanted to say about one of my undergraduate students. He just received a North Carolina space grant to actually investigate how much oxygen is needed to shut down this source of phosphorus to the biosphere. And that's my student there, Stephen Lale. It's a senior year. So just to summarize here, seafloor weathering under anoxic conditions represent a potentially significant source of bioavailable phosphorus. Dependence of seafloor phosphorus flux on atmospheric oxygen concentrations introduces a negative feedback mechanism that may be important for regulating atmospheric composition on water-rich exoplanets. And that future work will be focused on what degree of atmospheric-oceanic oxygenation is needed to shut down the source of phosphorus from seafloor weathering. And thank you for your attention. That is the end of my talk. So we have plenty of time to go over things.
Can't hear you, Maxime.
Yeah, okay, thanks, Raj. Yeah, I was saying thanks a lot, Drew, for this great talk. If you have questions, you can raise your hand on the Zoom hands, or you can write them down in the Q&A section, and we will read them. So I already see a few hands. Mark, you can go on.
Hello. Very interesting talk. I guess I was wondering, you can also oxidize iron with water, right? I guess it's like the serpentinization type reaction. I appreciate that it's sort of very different temperatures. But I guess I was wondering if you thought at all about like when that transition occurs, like when you might be able to make iron oxides and adsorb phosphorus even under anoxic conditions.
So you're thinking more of serpentinization processes, just to be clear?
But yeah, it's just an example of like oxidation of iron by water.
Yeah.
Another way to make iron oxides.
No, that's a very good question. Or even like photooxidation is another mechanism for that. But if you're in the deep ocean, I guess that won't be a case. So yeah, I mean, for instance, when I think about serpentinization, you can eventually serpentinize the crust to such a degree that it becomes completely oxidized, and that any phosphorus released from that alteration would never leave the seafloor. But yeah, that's what we're trying to figure out right now is actually what is the actual limit, whether basically oxygen concentrations will shut down this basically source of phosphorus. So I'm not giving you a clear answer, but that's basically as best I can give you at this moment in time. Thank you.
Thanks.
Right, I think Duncan, you're on.
Thanks, Maxime. Thank you, Drew. Really very much enjoyed your talk. Really interesting stuff. I had a question about the first part.
Sure.
With respect to the hydrothermal fluids and the way their compositions interact with seawater changing in terms of kind of depth of interaction, would changes potentially to like oceanic crust thickness through time, whether because of the temperature of the mantle or some other, tectonic factor, would changes to the thickness of that zone of interaction have similar type effects? So would we expect some sort of secular trend as people have discussed for things like the thickness of ocean crust through time?
Yeah. So yeah, I would imagine if, like, and I could be wrong, but like if I would imagine if you have a higher mantle heat flux and you're still allowing some type of partial melting to take place, that you would have more fast spreading ridges and a much higher flux of metals being distributed or delivered to seawater, with a lot less of those metals and sulfur being retained in the oceanic crust. So with regards to the lithosphere thickness, I didn't mention it, but basically, yeah, the intermediate and slow mid-ocean ridge hydrothermal systems have thicker lithospheres relative to faster mid-ocean ridge environments. Did I answer your question? Is that good?
Yeah, thank you.
Right, we have a question in the Q&A section, so I'm going to read it. A question by Adam Thomaston. How would including a high level of CO2, like in the Archean, in the simulated atmosphere affect the anaxic weathering of MORB?
Yeah, I guess it would basically enhance the weathering of the weathering at the seafloor, especially if bottom water temperatures have increased to some degree. That's what I would say.
Right, there's someone have another question. Well, I guess if not, then we thank Drew again for this great talk. And oh yeah, I guess Adam has a follow-up question. I'm gonna allow you to talk.
Sure.
Hi, yeah, can you hear me okay?
Yes.
All right, just a follow-up question for that. Could you comment on why you chose to do a N2 and H2 atmosphere for your experimental design?
Yeah, so basically the hydrogen's there because in the anoxic chamber, there's these platinum catalysts that if any oxygen gets into that chamber, it reacts with the hydrogen on the platinum catalyst. And so it's just part of the fill gas of the experimental design. With regards to there not being a platinum catalyst inside my reactor, that reaction isn't taking place. It's just there as a reducing agent in general.
Cool, thank you.
Yeah.
Right, any last minute question? Okay, well, if no, then again, thank you, Drew. And yeah, so if you want to watch this talk again, it's gonna be uploaded on the YouTube channel. And yeah, see you everyone in 2 weeks for the next seminar. Bye.